In previous lecture, we had discussed about multi-level feedback scheduling algorithm. Now in this lecture, we will understand the multi-processor scheduling. So what is the meaning of multi-processor scheduling? What are the different system architectures we have and how those architecture works? We will understand in this lecture. A multiprocessor scheduling, the multiprocessor refers to the system that provide multiple physical processors. So as we are saying that the multiple processor, right? So multiprocessor means multiple processor means more than one processor in a system, right? So therefore the term multiprocessor refers the system that provide multiple physical processors where each processor contain one single core CPU. So however, the definition of multiprocessor has evolved significantly, and on modern computing systems, multiprocessor now applies to the following system architecture. So we will understand these four types of system architectures based on this multiprocessor scheduling. Right. So multiprocessor means multiple physical processors, right? Each physical processor may contain one single core CPU. Okay, so in modern computing system, the multiprocessor now applied to the following system architecture. So we can see the modern computing systems have multi-core CPUs, multi-threaded cores, NUMA systems, heterogeneous multiprocessing systems. So before we indulge into the multi-core CPU, multi-threaded cores, NUMA system, heterogeneous multiprocessing. So talking about these system architectures. So first of all, understand multiprocessor scheduling approaches. So we have two approaches to multiprocessor scheduling, that is asymmetric multiprocessing is a simple because only one core accesses the system data structure, reducing the need for data sharing. So in the asymmetric multiprocessing, only one core of the processor accesses the system data structure, which reduces the need for data sharing. The downfall of this approach is the master server because a potential bottleneck where overall system performance may be reduced because of one core accessing the data structure and reducing the need for data sharing in this approach. So therefore the downfall of this approach is the master server because the potential bottleneck where overall system performance may be reduced in asymmetric multiprocessing. And coming to the standard approach for supporting multiprocessor is a symmetric multiprocessing, in short SMP, where each processor is self-scheduling. So there is no master server, so there is a self-scheduling processor. So each processor is a self-scheduling processor, and scheduling proceeds by having a scheduler for each processor examines the ready queue and select the thread to run. Means in this SMP, scheduling proceeds by having the scheduler, right? So scheduling is proceed by having the scheduler for each processor, right? If there are multiple processors, so for multiple processors there are multiple schedulers. So for each processor there is a scheduler that examines the ready queue and select the thread to run in that processor. So this approach is called as symmetric multiprocessing, which is the standard approach for supporting multiprocessors. Now we have two possible strategies for organizing the threads eligible to be scheduled. So what are the two possible strategies organizing the thread eligible to be scheduled? The first is all thread may be in common ready queue. Other approach or other strategy is each processor may have its own private queue of threads, right? So we are organizing the threads which are eligible to be scheduled in these two possible strategies. One says that all the thread may be in a common ready queue as described in a diagram. This is the common ready queue, right? So all the threads means T0, T1, T2 dash dash Tn, all the threads may be in a common ready queue. So this is the common ready queue what we are having. So this is the first possible strategy for organizing the threads eligible to be scheduled. And thereafter, so this a ready queue is assigned to core not, core 1 dash dash core n, right? And the second possible strategy for organizing threads eligible to be scheduled is each processor may have its own private queue of threads, means every processor, right? For example, say core not processor, core 1 processor dash 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 n number of cores are there, n number of processors are there, so core n process. So per core run queue means for every core there is a private queue, right? So every core there is a private queue. So in this fashion the threads eligible to be scheduled. So for every processor there is a separate queue, right? But in first example we have said that the common ready queue is prepared for all the cores, or we say that processor, right? So the common ready queue is prepared for all the processors, whereas in per core run queue, so all the processors there is a separate queue is prepared, so that separate queue is called as private queue of each processor, right? So these are the two possible strategies for organizing the threads eligible to be scheduled. Now coming to the system architecture in multiprocessor environment is the multi-core CPU. So multi-core CPU or multi-core processor. So traditionally we say that symmetric multi-processor systems have allowed several processes to run in parallel by providing multiple physical processors. The meaning is this SMP system have allowed several processes to run in parallel, because in symmetric multiprocessor systems which allows several processes means n number of processes can run parallelly by providing multiple physical processors. However, most contemporary computer hardware now placed multiple computing cores on the same physical chip, resulting in multi-core processor. So even I have described this concept in thread chapter. So I recommend those who have not seen my previous lecture on the thread, go back and kindly see those lectures. So there I have explained about the multi processors also, single processor also, single core and multi core also. So what happens when contemporary computer hardware now places multiple computing cores, means there is a one physical processor, but that physical processor might be having two or more core on the same physical chip. That is the meaning of this. Means physically there is only one chip or CPU in my computer, right? But it may having a two cores, means every core act like a CPU. So two core means it can simultaneously run two processes, right? So that is the multi-core processor. Okay, so multi means more than one, core means physically there is one processor, but that is logically divided into two, means the two processors are there but physically look like one. That is multi-core processor. So this symmetric multi-processing system that use multi-core processors are faster and consume less power than the system in which each CPU has its own physical chip. Means when we talking about this, multi-core processors are faster and it also consumes less power than the system in which each CPU has its own physical chip. Assuming that let us take an example of a processor, right? Physically there is only one processor and logically that is divided into four core, right? C1, core 1, core 2, core 3, core 4. Now what happens? Physically look like one CPU, but there are four CPUs, four processors. Okay, so it works faster and consumes less power. So converting this into one processor having one core means we should have four physical processors which having a single core. Okay, now we have single core C1, C2, C3, C4, right? So we have four physical processors, right? So now what happens? It doesn't work faster and it consumes more power. Okay, so therefore we are saying that symmetric multiprocessor systems use the multi-core processor like one physical processor, but there are multiple cores in it, right? So it works faster and consume less power. Now coming to this, multi-core processors may complicate scheduling issues, right? So may complicate scheduling issues means researchers have discovered that when a processor accesses the memory, it spends a significant amount of time waiting for the data to become available for it. So this situation is known as memory stall, because the processor is accessing the memory but it is spending significant amount of time waiting for the data to become available to it. So this situation is called memory stall and occurs primarily because the modern processors operate at much faster speed than the memory, right? So always the CPU, or we can say that the processors of the modern computers works much faster than the memory. So for that, what we do is we have a remedy, right? We have a remedy. So let's first understand this figure, right? And find out multiprocessors may complicate scheduling issue. So how they complicate the scheduling issue? Because there is a compute cycle and memory stall cycle. So memory stall cycle, so we have just only seen that the memory stall is nothing but a processor which accesses the memory, it spend lot of time waiting for the data to be available to it. So that is called memory stall. Okay, and this is primarily because of modern processors, because modern processors works at a much faster speed than the memory. Now any thread which enters, right, first it computes the cycle, then it wait for a memory, then the memory stall cycle, then again it goes to compute cycle, and then again waits for memory stall cycle and gets the memory stall cycle, and thereafter it computes the cycle, right? So this will continue, it will keeps on going by the time. Okay, so to solution to this problem is there is a remedy to this situation. Many recent hardware designs have implemented multi-threaded processing in which the two hardware threads are assigned to each core. It means that for in each core, right, in each core there are two hardware threads. Why the two hardware threads are given for each core we will understand, because to resolve this problem and to this thread to be executed continuously in compute cycle, and it should not wait for memory stall, because the processor which is accessing the memory, it is spending a lot of time for waiting for the data to become available to it. So that waiting period is a memory stall cycle, right? Significant amount of time is getting wasted in this memory stall cycles, right? So for handling this situation, uh, many recent hardware designs have implemented multi-threaded processing in a such a way that the two hardware threads are assigned to each core. Okay, so let us understand here. Okay, so that this remedy we can find in the multi-threaded cores. So multi-threaded core means a multiple threads are there in a single core. As I explained in this last line, a hardware threads are assigned to each core, means the two or more hardware threads are assigned to each core, means in every core we can have two or more hardware threads. Okay, so this is the solution what we have for this multi-core CPUs. So therefore the second system architecture is the multi-threaded cores. So in this multi-threaded core, the Intel processor used the term hyper-threading, which is also known as simultaneous multi-threading or SMT. I recommend you to go back and watch my third chapter video on thread, the thread concept, creating the thread, terminating the thread. So there I have explained about this concept also, simultaneous multi-threading. Right. So what is mean by thread? What is single thread? What is multi-threaded process? How it works? And what is the meaning of simultaneous threading? Okay. So this simultaneous threading to describe assigning the multiple hardware threads to a single processing core, means we have single processing core. Okay, single processing core, and that single processing core have multiple hardware threads, right? So this contemporary Intel processor such as i7 support two threads per core, means in every core we are having two threads, right, which supports two threads. Let's have T1 and T2. This is the core. Okay, every core in i7 supports two thread per core, while the Oracle Spark M7 processor support 8 threads per core, means in every core it support 8 threads, right? It support 8 threads, T1, T2, T3, T4, T5, T6, T7 and T8. Like this, in every core there are 8 thread are supported, means 8 threads per core with 8 core per processor, means we are having 8 core in a single processor and every core supports 8 threads. It means that total 8 into 8 64. So thus it provides the OS with 64 logical CPUs. Means we can achieve 64 logical processors because we have 8 core and every core is having 8 threads. So every core is having 8 threads, right? So that is 8 into 8 equals to 64. So 64 logical CPUs. Okay. So that way, if one hardware thread stall while waiting for memory, the core can switch to another thread. Now assume that thread 1, right? The thread 1 and thread naught is there. So thread naught is in computing cycle, then this thread is waiting for memory stall. The other thread can go for the compute cycle. So in this fashion, right, if one hardware thread stall while waiting for memory, the core can switch to another thread. So like this, one thread is waiting for memory, then the core can switch to another thread. So in this fashion, this multi-threaded core works. Okay. And in multi-threaded core, we have coarse-grained multi-threading. A thread executes on a core until a long latency event such as memory stall occurs. Because of the delay caused by long latency event, the core must switch to another thread to begin execution as shown in this figure. Okay. Fine grained multi-threading, the architectural design of fine grained system which includes the logic for the thread switching. As a result, the cost of switching between the thread is small. So here the cost of switching between the thread is becoming small, and here we get the long latency event. The core switch to another thread to begin its execution in coarse-grained multi-threading. So these are the two things which I want to explain in this multi-threaded cores, right? Coarse-grained having a long latency event, core must switch to another thread to begin execution, whereas in fine-grained multi-threading architectural design, a fine-grained system which includes the logic for the thread switching. As a result, the cost of switching between the thread is becoming lesser. Okay. Now, an operating system perspective, each hardware thread maintains its architectural state such as instruction, pointer and register set. So as an operating system perspective, we are talking about the each hardware thread, means every thread maintain its architectural state, like it maintains its instructions, pointers and register sets. This was also mentioned in my previous lecture in the third chapter, the thread concept. So if you go back and watch that video, you will get the idea about the thread and all the hardware, every thread which maintains the hardware like instruction, pointer and register set, stack, etc. So such as instructions, pointer, register set, and thus appearing as a logical CPU that is available to run the software thread. So this technique is known as chip multithreading, which is also called as CMT, right? So this technique, the hardware thread which maintains the architectural state such as instruction, pointer, register set, and thus appearing to a logical CPU that is available to run the software thread. So this is called chip multithreading. So here you can get the processor, right? It is a physically one processor, and there are 4 core we have, and every core is having 2 hardware thread, as I explained in the previous slide. Here multiple hardware threads to a single processing core. Okay, so in single core we have multiple hardware threads. Okay, now in operating system view, operating system view is there are logically 8 processors, right? Physically there is only one processor, and processor is having 4 core, and every core is having 2 hardware threads, means each core executes 2 threads parallelly. So hence we can achieve 2 here, 2 here, 2 here, and 2 here. So altogether 8. So in operating systems view, it's look like 8 CPUs are working. Okay. Okay, the third system architecture in multiprocessing systems are NUMA systems, right? NUMA systems. It is a hardware architecture where the processor have varying the access times to different memory location. So NUMA systems are the hardware architecture where the processors have varying the access time to different memory locations. Why we are saying different memory location? It might be a local node or it might be a remote node. So therefore we are saying that access time might vary, okay, because of different memory locations in NUMA systems, because NUMA is a hardware architecture. It is not a software, it is a hardware where the processors have varying the access time. So when the processor accesses the instructions or looking for the data, the access time may vary because of different memory locations. Now what happens in this NUMA system? Uh, this is in contrast to uniform memory access. Uniform memory access means memory is resides in a single node and the CPU or the processor is accessing that memory. A system where all the processors have the same access time to all memory. Uniform memory access means all the processors, right? Multiple processors having the same amount of access time to all memory, which is called UMA, uniform memory access. But we are talking about NUMA, right? NUMA. So non-uniform memory access. We are talking about non-uniform memory access. So we are added non here. So therefore it is called as NUMA, non-uniform memory access, right? So what happens in these kinds of system architecture? NUMA system provide the performance by allowing the processor to access memory closer to them more quickly, reducing latency and contention. So what is the meaning of reducing the latency and contention? Means when the NUMA systems improve the performance, they will allow the processor to access the memory closer to them more quickly. Means any memory which is closer to the processor, right, which is closer to the processor in the NUMA system, which reduces the latency time and also increases the contention. So let us understand by this diagram. Okay, so I will directly jump to this diagram. Now there is a CPU, right? There is a memory which is accessed by this CPU. So we are saying that fast access. There is another CPU, right? Another CPU So this is another node we are having, and it also having a memory. So this CPU can access this memory faster. But assume that this CPU wants to access the memory of another node, right? Then it is getting slow. So slow access. Okay. Now I will come back here. Okay. So I will come back to this NOMA system. So the access time to different memory locations. So we are accessing the different memory location. So therefore we are getting more access time, or we are saying that varying the access time. Okay. So by optimizing the memory access based on the location, NUMA system can significantly improve the performance, especially in large-scale multiprocessing system. This is particularly beneficial for workload where the memory access locally is high, right? Locally or locality is the high. The memory access locality is high for a local memory, meaning that processor tend to access the data with their own node. What happens here? The CPU is accessing the memory of the same node, where it is accessing the memory of the another node. That time it is getting slow, right? So that is the meaning of this. Okay. So where access locality is high, meaning that the processor tend to access data within their own node, then only it locality becomes high and access of the memory becomes high. When it accesses the memory of the other node becomes slow. Now an architecture featuring the NUMA, where there are two physical processor chips, each with their own CPU and local memory, right? So own CPU means every node is having own CPUs and they have their own local memory, right? Now, although a system interconnected allows all the CPU in NOMA system to share one physical address space, a CPU has faster access to its local memory than to memory local to another CPU. So that is shown here. Okay. So it can access the local memory faster than the other memory of the other node. So even though it is interconnected. Okay. If the OS, CPU scheduler and memory placement algorithm are NUMA aware and work together, then a thread that has been scheduled onto a particular CPU can be allocated memory closest where the CPU resides, thus providing the thread the faster possible memory access. So this can be happen. Okay. Now the fourth system architecture in multiprocessing systems are the heterogeneous multiprocessing. So in heterogeneous multiprocessing, the mobile systems now include multi-core architecture. Some systems are now designed using multi-core that run the same instruction set yet vary in terms of their clock speed, power management, including the ability to adjust the power consumption of a core to the point of idling the core. Such systems are known as heterogeneous multiprocessing systems. Now in mobile systems, what happened? Multi-core, it is having a multi-core architecture, means some systems are now designed using the core that run the same instruction set, yet varying in terms of their clock speed. Even though there is a varying in the clock speed and power management, it is the having the ability to adjust the power consumption of the core to the point of idling the core and actively working the core. Such systems are known as heterogeneous multiprocessing systems. The intention behind this heterogeneous multiprocessing system is to better management of power consumption by assigning the task to a certain course based upon the specific demand of the task. So based on the demand, the certain cores are consuming and assigning the work and consuming the power, and remainings are sitting idle, so that it is a better management of the power consumption by assigning the task to a certain course, right? Certain core based upon a specific demands of the task. Now there are certain advantages of this heterogeneous multiprocessing. There are several advantages to this approach. By combining the number of slower cores with the faster ones, the CPU scheduler can assign the tasks that do not require high performance. Means by combining the number of slow core with the fast one, the CPU scheduler can assign the tasks that do not require the high performance but may need to run for a longer period, such as background tasks are assigned to a slower core to little core, thereby helping to preserve a better charge sorry battery charge. Similarly, interactive application which require more processing power but may run for shorter duration can assigned to a big core. So Windows 10 supports this heterogeneous multiprocessor scheduling by allowing the thread to select a scheduling policy that best support its power management demand. So this is all about the multiprocessing scheduling algorithms, right? So how the multiprocessor scheduling works, the meaning of the multi-scheduler, and we have a system architectures like multi-core CPUs, multi-threaded cores, NUMA systems, and heterogeneous multiprocessings. Hope you understood this concept. With this concept, we conclude this chapter and we will come up with the next chapter in the next lecture, that is process synchronization. So it is one of the most important topic in operating system, process synchronization. So thank you for watching. See you in the next lecture.